So I haven't gotten your feedback. I presume you have the software. So I shared the link. So unless somebody had a problem with installing the software, then you should have pointed out even before the meeting. So for today, we are going to cover the following. We're going to do fundamental of PLC programming. And these are some of the things you're going to learn: how to convert a simple electrical ladder diagram to a PLC program, difference between physical components and the program components, and why we're using PLC cells on number of physical components, how to construct disagreement and majority circuits, and how to construct special purpose logic in a PLC program. So let's go into the introduction part. So when writing programs for PLC, it's beneficial to have a background in ladder diagramming for machines. So in essence, I'll just explain what the introduction means. So you need to actually understand ladder diagram and basic circuit components. And you also need to relate the physical components versus the program components. So that's something also you need to understand for you to be able to relate well with the programming. So you need, at least you need to know a little bit of electrical knowledge and symbols. These are relays. Another thing you need to know is binary logics: the AND gate, the OR gate, the NOT gate, the NAND gate. Yeah. For those who are totally new to maybe the Boolean algebra, the AND gates, the NOT gate, the OR gate, if somebody has a problem, you can just be able to raise it up and we can help you out for that. But I know for those who are doing maybe engineering or computer science, they already know these things. And if you're passionate about science, you definitely must be knowing something about logic gates. So what we are going to do in this lesson, we'll take our foundation knowledge learned in chapter 1 and easy to beat understanding of PLC programming. So the programming method used in this chapter will be the graphical method, which uses schematic symbols for relay coils and contacts. Then later in the chapter, we'll discuss another method which uses mnemonic language. That's advanced method. So we may not be able to cover that, but at least maybe you can get a hint of what that looks like. So just another thing, maybe why it might be there are a few challenges students encounter. Maybe just trying to relate between physical components and program components. This is because maybe you might try to mix up between an electrical symbol and with logic symbol. But of course, here we are going to interpret the physical components and then we transfer them to the logical program, the PLC software. Yeah. So we are going to assume, and of course, this is what happens. The field are the components there, and you as the engineer, you're the ones doing the programming. So you are taking a physical component in the field and you are relating it to the program itself. So it's a one-to-one relationship. And so a programming component will not only have the same reference designator as the physical component, but can have the same name. Okay, so example, consider an normally open push button switch, maybe named S1. Okay, maybe you have on the door, it's named start. That is on the door of the maybe control panel. So if we connect this input to 001, that is the digital input of PLC 1, and then we program the PLC, the start switch will become normally open, relay contact, with reference to the designator IN01. That means it's input 001. And then you assign it a name which is start. Same name you assign to the control panel. Maybe you have a control panel and yet has a push button. So the same push button you say start or run, you name it exactly the same thing you name it in the program for your consistency and also for ease of reference. It's good. It's a good practice and widely advised to do that, so that if you're coming even to troubleshoot a program, you already know that this input is the same as what is on the sensor. If maybe it's a pressure sensor, just write pressure sensor, and even maybe give more details. Pressure sensor, which range, 0 to 16 bar, or 0 to 5 bar, that kind of things. So it becomes easier for you to relate them in the field. If you give them arbitrary names, maybe you say switch 1, switch 2, switch 3, you'll have a big problem because you don't know. You have maybe in a control panel, you have like 20 switches. So if you start naming them like switch 1, switch 2, but on the control panel itself, they have been given you maybe this is pump 1 start, pump 2 start, pump 3 start, pump 4 start, pump 5 up to pump whatever, or even maybe fan 1 or regular 1, or compressor. Just name it compressor switch 1. This is compressor switch 2, or compressor start, compressor stop, compressor emergency stop. So that's some of the things you need to name. Exactly the same name you give them on the field equipment is the same name you're going to assign these items. It won't be any different from that. It will definitely be the same thing, and that becomes easier for you to actually interrelate items, yeah, as you do your programming. So as a programming example, consider I'm just reading this statement, I was just giving you a brief. So as a programming example, consider the simple circuit and circuits shown in the figure below. Consists of two momentary push buttons in series with a lamp. Although it would be very uneconomical to implement a circuit this simple using a PLC, for example, this is what we want to do. When we convert a circuit to run on a PLC, we first remove the component from the original circuit and wire them to the PLC as shown in the next figure. One major difference in the circuit is that two switches are no longer wired in series. We see that in the next diagram. Instead, one is wired to a separate input on the PLC. As we will see later, the two switches will be connected in series in the PLC program. By providing each switch with a separate input to the PLC, we gain the maximum amount of flexibility. In other words, by connecting them to the PLC in this fashion, we can wire them in software in any format we wish. So this is what we mean. So you have, so these ones, so say this one maybe is going to be your input 1 and common, because there are two contacts. Even the same way you do for Arduino. You take 12 volts, you put it on the input, or you take 0 volts and you put it the input. So you have two reference. One goes to the digital input, another one goes to the common, which is your common terminal. That is like a reference terminal. And this is how it looks like in a PLC. So you have your reference terminal, and then your input is when you connect power, it now energizes and the lamp goes out. So this is basically what you are used to seeing. And the same thing is what happens in any PLC programming environment, or wiring for that matter. Yeah. So another thing is, of course, for the output. So like what the circuit means. So once we know how the external components are wired to the PLC, we can then write our program. Okay, just reading this statement. And in this case, we need to connect the two switches in series. However, once the signals are inside the PLC, they are assigned new reference designators, which are determined by the respective terminal on the PLC. Maybe switch 1 is connected to input 1. It's another one connected to input 2. Maybe the lamp is connected to digital out or Q 0.0, as you will see in the programming example. That may be for the programming guys, for the practical session, you'll be able to understand what I mean by this. And this is how you wire it in the PLC program, right? You have input 1, input 2, and they're in series. And then you have your bulb here. So just take a look. I need you to just figure out and understand what that means, and we give you 2 minutes to reflect and just try to reason with the circuit, see what the circuit means and the symbolic and the PLC program, how it looks like. So of course in the actual PLC program, we don't have the dotted lines. We have continuous lines. This is just a printing error, and then this is just a printing by the plotter. But of course in the PLC we don't have continuous line. The dotted lines, it's just continuous. So don't get scared about that. So here we have only one RAM, which you can see. So that's said and done. Let's move to the next thing. So when the program in figure 3.3 is run, the one you've seen above, the PLC first updates the input train image by storing the values of the inputs. I told you about the scan time yesterday, and also the scan period and the cycle time. Yeah. So during startup, it checks on the outputs, and the input then stores them in the input register. Then it solves the ladder diagram according to the way it is drawn and based on the contents of the input image register. For our program, if both input 1 and input 2 are on, turns on output number 1 in the output image register. Careful, it does not turn on the output terminal yet. So keep that in mind. Then when it is completed solving the entire program, it performs another update. This update transfers the contents of the output register image, the most recent results of solving the later program, the output terminals. This turns on terminal out 1, which turns on the lamp 1. At the same time, it transfers the contents of the output image register to the output terminals. It also transfers the logical values of the input terminals to the input image register. Now it is ready to solve the ladder again. So now once it's done, it now does another scan cycle and another one and another one, and up to the infinity. It will continuously be doing the scan cycles depending on the cycle time. And we remember we said what cycle time is. We're talking about nanoseconds here. These are some of the fastest PLCs, nanoseconds, maybe in 5 or 10 nanoseconds. Others, of course, we have milliseconds, 500 milliseconds, or 40, 50 nanoseconds. Yeah. So next we'll add another lamp. That's another RAM on either switch 1 or 2. So if you want to add this circuit in our lecture, we would have the circuit. So this is the electrical representation for information. And then when that is done, this is now the PLC wiring procedure. Of course, we're maintaining the same input because we're picking from the same terminal. Okay, so here, look here. The wiring diagram to implement both AND and OR circuits shown in the figure 3.5. Notice that here the only change we've made to the circuit is to add lamp 2 to the PLC output. Since the switch S1 and S2 are already available inside the PLC via the inputs IN1 and input 2, so it will be redundant to again include other switch contacts, yet they are the same switch performing the same function. So that means you save space in terms of inputs and you reduce your wirings inside the PLC. That's the advantage of using PLCs. So this reduces the cost because even though our program will require more than one contact of IN1, input 1 and input 2, each of the actual switches that generate these inputs 1 and 2 only needs a single contact from the PLC terminal. That's how it looks like. So you just add the output and the signal, the other signals you maintain. Yeah. So that means we just need to add the rung as below. Ignore the dotted line. Take it like another line. So now we now want to complicate the circuit more. Okay. And we add 4 lamps and include other switches. Okay. Just study the circuit. Try to imagine how that circuit would be done. Good. So that's some time that I gave you to figure out and understand. So once, of course, this is the electrical connection. Now go to the rungs. And this is the rung, how it looks like. So that's how the PLC program will look like. Okay. So we move on to the example 1. And I wish somebody could be able to do this example, but I don't know if anyone of you can be able to tackle these. Yeah. So they're telling you a lighting control system is to be developed. The system will be controlled by 4 switches: switch 1, switch 2, switch 3, and switch 4. These switches will control the lighting in the room based on the following criteria. Any of 3 of the switches. I need some of you to write this. I need you to type in a notepad. Type for me the logic representation. That is the statement representation. Maybe you say lamp 1 to lamp 1 is equals to this switch 1 plus switch 2 plus switch 3 plus switch 4 in a format. Then you can paste it on the chart. Then we can see if it's one of making people also active, also learning by doing. Because for PLCs you have to practice. Yeah, there's no shortcut. It's like mathematics. You have to practice. You have to get the logics and analyze them. So I want you to check this task and try and draft something. Then we can see if one of you has come up with something. It should take you a very short time. And I think all of you can see the screen. So it says a lighting control system is to be developed. The system will be controlled by 4 switches: S switch 1, 2, 3, and 4. These switches control the lighting in the room based on the following criteria. So you have 1 lamp. Any of the 3 switches, 1, 2, 3, if turned on, can turn the light on. but all three switches must be off before the lighting will turn off. Okay? That's something you need to figure out. Logic 2. The fourth switch 4 is a master control switch. If this switch is in the on position, the lights will be off and none of the other three switches have any control. Problem. Design the wiring diagram for the controller connections, assign the inputs and outputs, and develop the ladder diagram which will accomplish the task. Okay. So, can any one of you have an idea? I don't know if WebEx has, people can be able to raise hands. I don't know if it's like Zoom where people can raise hands. Those that think they have an idea. I don't know. I think there's a lot of raising hands. Please annotate. Don't know about it. So any attempts?
Okay.
Hello, can I attempt?
Yeah, any
So,
attempts from anyone?
okay. So for
Yeah.
the first logic, the one that says any of the three switches, switch 1, switch 2, and switch 3, if turned on, can turn the lighting on. So that means switch 1, switch 2, and switch 3 are odd, but they are normally closed. That means if the coil is energized, the lamp will light any of the three switches. And then for switch 4, it is the master switch, but it is a normally open switch, normally open relay. So that means if the power is not supplied to the relay, the other switches will be, the other switch 1, switch 2, switch 3 will be off. I think so. But it will be and to the other switches. Yeah.
So you said the switch 4 is normally open or normally closed.
Switch 4 is normally open, I think, yes.
What about switch 1, 2, and 3?
Normally closed.
Normally closed. Okay. So you know the logical representation of the normally open and normally closed.
Yeah.
So how does a normally open look like and the normally closed look like?
Normally open doesn't have a cross in between the hash. Okay. It
Yeah.
doesn't have the cross, but then for the normally closed, it has something like a cross.
All right, so you've given a good attempt, but you've failed on the normally open and normally closed. Any other trial from any other person? That's a good trial.
Okay, let me try. Can I try?
Yes, please.
Yes, please. Okay. Switch 1, switch 2, and switch 3 should be normally open, yeah? Then switch 4 normally closed. Then switch 1, switch 2, and switch 3 should be there. Then then the three with to be ended with switch 4.
Yeah, correct. So Beryl, you've seen why you made a mistake, right?
You made a mistake, right?
Yes, I've seen.
Yeah, because the switch 4 will act like an emergency stop, right? So that when you press it, it disconnects the entire circuit. So let's go and see what it looks like. So this is just theoretical, which I know you've understood the way you've tried to explain it. Yeah, and that's the circuit, right? So Beryl was very right, but I know the logic, the NO and NC. These are very confusing, but yeah, you need to try, and these are some of the things that will actually, they may cause a problem, a bug in a PLC program, because that's like an instruction. So if you're not careful, you might end up creating a bug within a program, which may really be a bit of challenging. So good try, guys. I think we are on the right track. So I think even once you get the software, we start doing the software demo, it's going to be very easy. So let's just, like what I said, a normally closed contact represents an inversion of the assigned element, in this case, input 4, which is defined as switch 4. So in the off position, switch 4 is open. This means that input 4 will be off or de-energized. In order for an element to be assigned to input 4 to be closed with a switch in the off position, it must be shown as a normally closed contact. When switch 4 is turned on, the input 4 will become active, and input 4 is on, a normally closed contact, input 4 will open. With this contact open, none of the other switches will be able to control the output. Remember, a normally closed switch will open when energized and will close when de-energized. So that's how the emergency stop or the safety function works. Yeah, so that's it. And this is just Boolean expressions, but I don't want to go into that. This is an XOR, but I don't want to go into that. It just will be a bit of heavy for people who didn't do digital electronics, and we're quite heavy on them. So like we're proceeding on well. So I'm going to another circuit. So there are situations in which a PLC must take a decision based on the results of a majority of inputs. For example, assume the PLC is monitoring 5 tanks of liquid and must give a warning to the operator when 3 of them are empty. It doesn't matter which 3 tanks are empty, only that any 3 of the 5 are empty. It's saying it should give a warning to the operator when 3 of them are empty. Okay, when 3 of them. So there are 5. Okay. So the result, it turns out that using binomial coefficients, there are 10 possible combinations of 3 empty tanks. Therefore, there are also combinations of 4 empty tanks and the possibility of 5 empty tanks. But as we will see, those cases will automatically be included when we design system for 3 empty tanks. So it's important, it's worth noting that when designing majority of circuit, design them so that votes of more than a margin majority would be accepted. For example, let's assume that our 5-tank example, the tanks are labeled A, B, C, D, and E. When an input from a tank is on, it indicates that the tank is empty. Okay. So one combination of 3 empty tanks will be tanks A, B, C, empty, and D, E, not empty. In this, if this is expressed as a Boolean expression, it will be A, B, C, D, ANDed, D, and D noted, D noted, E noted. However, this expression will not be true if A, B, C, and D were on, nor would it be true if all inputs were on. However, if we leave D and E as don't cares, it would take into account these possibilities. Therefore, we would shorten our expression to ABC, which would cover conditions ABC, D, don't care, E, don't care. Okay, and ABC, D, E, noted, or ABC, D, noted, E, and ABC all, which will be majority conditions. So it turns out that if we write our program to cover all these conditions of 3 empty tanks, and each expression uses only 3 inputs, we will cover, by virtue of don't cares, the 4 combinations of 4 empty tanks and 1 combination of 5 empty tanks. So to find all possible combinations of 3 tanks out of 5, we begin by constructing binary table of all possible 5-bit numbers beginning with 0 and ending in 1111. And we assign each of the 5 columns to one of the tanks. To the right of the columns, we make another column, which is the sum of ones in each row. When completed, the table will appear shown. So this is what is meant. So you have your 3 tanks ABC. And then you come up with possibilities. Of the tank being empty. And then this column is the addition of these values. These are the possibilities. So I hope you remember this logic. Remember this. Just trying to give you a this is a truth table. I don't know how many of you have done digital electronics or you understand Boolean circuits. I don't know if you understand Boolean circuits, Boolean logics. But a truth table is a table. Let me just do a draw one. Like if you want to draw a truth table for an OR gate of 2 inputs, I begin with A, B, and the result. So this is my out. So we will start with 0, 0, 0, 1, 1, 0, 1, 1. Okay. That's the first step. Then, how do we generate a 4-bit number? Let me start again. Let me pick another big column. If I want to generate a 4-bit input, let me start with 3. I start with A, B, C, and I do that. And this is out. So how do you generate, if you have 3 inputs, how you generate the columns? Okay. So the number of columns is always equal to 2 raised to the power of the number of inputs. So if you do 2 raised to the power of 2, do 2 raised to the power of 3. This is for generation. Just so for your case, you have how you just do this basic. You always start with this basic 2 inputs. This is the basic. You start with 0 0. I'll show you how you're going to proceed. Then you do 0 1. This one you can master this. I'm just giving you how to generate it very easily. Then you say 1 1. Once you've done this, you have four inputs. Okay. How to generate the next? The last, you add the zeros here on the first bit. Once you've done with the 2 inputs, you add here. And now the next column, you invert these. So assume in a truth table, there are things we call the LSB. And here we call it MSB. Most significant bit, least significant bit. So for you to generate the next column, you start with the most significant bit at the bottom and you write the inverted logic of the column you have. Once you've done this add zeros to the first 4, then start inverting it. 1 with MSB 1 0 0. Go to the next one 1 0 1. Go to the next one 1 1 1 1 0. Then go to the next one 1 1 1. Okay. So how many do you have? 1 2 3 4 5 6 7 8 columns. Okay. 8 rows. 1 2 3 4 5 6 7 8. How many inputs? 3 inputs. Okay. So 2 raised to the power of 3. What is the answer? Audience, 2 raised to the power of 2.
8. 2 raised power
That's
2 is
8.
4, and for 3, 8.
So what about 2 raised to the power 4? 16. So this is just basically how you generate these things. It's not magic. It's not anything. So now you have the first 3. You've already generated them. And now for the next 4. So these are 8. For the next 4, you add now zeros here. 0 0 0, 0, 0, 0, 0, 0. And now you want to go now to the next 16-bit numbers. You now start inverting this as the MSB. MSB, most significant bit. And now this will become your LSB here. And now you start with the 1, 0, 0, 0. Go to the next one, 1, 0, 0. Next one, 1, 0, 0. We're just inverting. Go to the next one, 1, 1, 0, 0. So that's how you generate the truth tables. So these are called truth tables. They help you to get combination of the circuits. So remember, if you have 3 tanks, A, B, C. Now we have A, we now have A, B, C, D. Let's take now this one like A, B, C, D. So if you have 4 tanks and either of the 3 tanks are on, like this scenario, when all the 3 are on, we give a signal. So we can go here to a logic requirement and we say to find all possible combination of 3 tanks out of 5. So that is how the logic was developed. It's not magic. It's just grasping a concept and working out the logics correctly. And this is how we develop for the 4 inputs. The 5th one, you can get, of course, a truth table for a 5th input. You approach it the same, but now you're going to encounter a lot of combinations. So here we're talking about how many combinations. These are so many combinations. 16 combinations. If you go to a 5 column, 5 column for 5 inputs, then of course the combinations grow. So this is how it was developed, and now we go to what we think. Then when we first into the table, find every row. So if you look at what we're developing there, we are developing this row, the whole of this row. This is what we developed. Okay, this is for the 4 inputs that we developed. Right. And then after we developed this one, we added this column, and this one was inverted as 1. And then there was an addition of all these combinations here. So this is a combination of all these. So we're just interested in 3 of the tanks. So if 3 tanks are on, you get, okay. So you see like here, 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 something of the sort. Now let's now proceed. If there's any question, if you have a problem, just mention it. Then, referring to the table, find every row that has a sum of 3. For each of the rows, write the combination of the 3 tanks for the row that is containing the ones. The 10 combination of 3 empty tanks that are C, D, B, E, blah, 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 like in the first case. So when we write the program for this problem, we can economize on relay contacts in our program. We should keep in mind that simplifying a complex relay structure will save on PLC memory space used by the program. However, if the simplification makes the program difficult for another programmer to read and understand, it should be simplified. It should not be simplified. We will simplify by factoring and then check to see if the ladder diagram is easy readable. We will factor as follows. So you have these combinations here. We started with CDBE. Okay. This was the first case, CDBE. Then we went to BDE. Okay. Another case we have is BCD. BC and E. This one. Another case, this one. Okay. And then other case is this one, SCE. So these are the combinations that we are talking about. And once you have all these combinations, they are going to be ORed and ANDed. So there's something we call K-map, which is used to reduce the logic inputs. So if maybe I'm talking of about, I'm giving you an industry like EABL where you have even 100+ sensors. You developing a logic will be very complex. So you need advanced tools for you to be able to develop that algorithm. Because if you approach it the way it is, like here, it will be very cumbersome. Even the logics will throw you out. So that's why sometimes you have to reduce them, you simplify the logics. So if you simplify this way, that already takes into account the whole of this circuit here. You can imagine how the whole of this line, this logic expression, takes the entire circuit. So it simplifies everything. That's why as a programmer, there are simplification tools that are there. The one is called K-map. You simplify a Boolean expression, maybe for an industry or something. So if you're given a very heavy, complex program, you have to simplify the inputs and understand how they are going to, you're going to minimize the programming, because it can be cumbersome for you. And if you don't do well, you might mix up the logics, and those relays and normally open, normally close, they will clash. And if you're having like a combination of these are all possible combinations. All these are combinations. All these are combinations. How many do you have? 32 combinations. So these combinations, if you don't do them carefully, if maybe you don't minimize, you don't simplify the combinations, you may end up having a bug. Maybe this one may be coming on, this one coming on, maybe it's mixed up, it's coming on again here, you find there's another task here. So this sometimes you have to be careful. You study the program, study the client needs, you understand the logic, then you draw the diagram. Once you've drawn the expression and you've simplified to the easiest possible mean that is available, you can now go and implement in such a format. And this is be tank 1, tank 2, tank 3. If this one is on, it will trigger. If this one, or this one on, trigger. This one, or this one, trigger. This one, or this one, or this one, trigger. This one, okay, this one and this one, and this one, trigger. This one and this one, and this one, trigger. This one and this one, and this one, trigger. This one and this one, or this one and this one, and this one, trigger. This one and this one and this one, trigger. This one, this loop is done. You go to the next loop. This one and this one, trigger. This one and this one route, trigger. This route, trigger. This one, you trigger again. So those are total combinations of possibilities of outputs, and that's how the tanks will be behaving. But if you write a very good program and you are able to simulate and understand the whole everything, then definitely you're going to be a very good PLC programmer. As long as you're able to minimize this circuit, very complicated, to a very simplified large circuit using the tools available. They have told you the one of the tools is called K-map. It's a very good tool. Other are just online tools that can maybe you can be able to even get combinations of 5. Just search maybe for you say maybe truth table of 5 inputs. Yeah. So if things become a bit, but you can approach it the way I've showed you, the 4. If you start with the 4, when you put the others as don't care, I mean, you first minimize them. Trying to see if I can get something for you. Most of them are 4. Maybe by I give you an assignment. Most of them are 4 inputs. So, like you said, if you really think you can try and reduce, first work with the 4 number, then the 1 number, you can approach it this way. Okay, you minimize it depending on the possibilities, depending on the condition of what you want to achieve. Then you are able to sort out the thing. Okay, so remember we had these column. So we had this column. So even if you can go to the 64, remember we added zeros here to get the 4th column. Then we started inverting this column. So when we inverted this column, this is what we got. And then you invert this column, this is what you get. You invert this column, this is what you get. You invert the 4th column, this is what you get. You invert the 5th column, this is what you get. And the sequence goes. So when you're done with this one, 16, when you're done with the 32 number, you'll have this column again, and this one is a long list. Once you're done with this list, you will now put again, add another zeros. 0 0 0 0 0 0 0 0 0 0 up to the 32th. So you start with the 0, another you add the 0 0 0 1 2 3 4 5 6 7 8 9 10 13 14 15 16 17 18 up to the 32th number. So you'll add all these zeros on this column, and then the next 32 number you now start inverting again. After adding the zeros, you now start inverting from the MSB, most significant bit, MSB, and the cycle continues. You'll go up to the 32 inputs, 64 inputs, 28. So I think that's the maximum. Then you can now use this simplification. You can now get the tool, KMap, just write these combinations, and you take a KMap, it can help you be able to solve. If you think it's so hard, just use these symbols here the way they are, without simplifying them further, if somebody will not be able to understand. But at least you know in the truth table, that's how it works. So we started with the 2 inputs. We started with these ones. Okay, we added zeros. We generated this one. We added zeros. We generated these ones. We added the zeros. We generated this one. When you're done with these ones, you add the zeros again, and then you generate the next 16 to get 32. And the cycle is like that. That's how you do digital analysis, depending on any number of inputs. But of course, if you have a lot of inputs, you can use tools which are there online, and say maybe you have 2 inputs, and then you say you want to do combinations of 2 are on 3, yeah, and then you can be able to get something. But of course, it's something you can do on your own if you're developing some simple circuits. So then when referring to the truth table, find every other that I think that's what we've already done. I've shown you how to generate that one. I think now for even those ones who don't know about electronics, you now be able to learn how the table is generated. It's just for you to take and just know the first 4 inputs to the four logic combinations of the 4 inputs of when you're having 2 inputs A, B, then generate 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. The rest is history. You just regenerate. So with the above examples, little or no discussion has been made of scan operations of timing. We have merely assumed that when all the conditions were met, for a call to energize it will do so. However, we must always be aware of the procedure the controller uses to solve the ladder diagram. As an example of how an understanding of scanning can benefit us as programmers, let's develop an oscillator. An oscillator in a ladder diagram world is a coil that turns on and off alternately on each scan. An oscillator can be useful to control things like math functions and other functions, which are controlled by a transitional contact. A transitional contact is a contact that switches from closed to open, from open to close. Functions such as math functions in some controllers may only perform the assigned process So functions such as math functions in some controllers only perform their assigned process function when on the one scan when the controller logic switch from open to close. As long as the control logic remains closed or open, the function will not be performed. To enable this function to occur on an ongoing basis, a transitional contact may be replaced in the control logic. So this is just like it's a relay. It's like setting and resetting. You set when the loop is done, you reset. When the loop is done, you set. When the loop is up, you reset. So it's like a set reset operation. But it's internal. It's internal. It's not like it's a logic that you just develop. Yeah. There are special coils within the PLC that are able to do that. They activate the math function or some logic combination of circuits, or maybe user developed functions. So when it goes here, it will reset here. When it goes on, resets. This one resets, starts again, check the next cycle. When it gets here again, resets. So it's like an ongoing circuit. So this is just like what we talked about, relay circuit, a hold-on circuit. But for you to reset, you have to press input number 2. Okay. So to the next thing. So a holding contact allows the programmer to provide for a coil which will hold itself on after being energized for at least one scan. Some instances in which such a configuration is required are on-off control occasions when a fault may occur for only one scan and must be detected at a later time. The coil could be latched when the fault occurs. Another name for such a rung is a latch, and the coil is said to be latched on by the contact associated with the coil. So as we develop these programs, of course, when the PLC hangs, if it hangs and it has not done a scan run and the output is still active, that's a problem. Yeah. So that's why you need to have those contacts in every run, the reset contacts, so that they provide some safety mechanism when you're doing this, if there's a problem in the PLC. Yeah. So placing this rung, so what they mean here, as programs develop, there are a number of times the contact is required that is always on. In your PLC, there is generally a coil set aside that meets this requirement. There are, however, some instances where the programmer will have to generate this type of contact in the ladder. One instance where such a contact is required is for a level trigger, not transition trigger, arithmetic operation that is to be performed on every scan. So most PLC require that at least one contact be present in every run to satisfy the requirement and have an always true logic. A contact must be placed in the run that is always true, always closed. There are two ways to produce such a contact. One is to create a coil that is always de-energized and use a normally closed contact associated with the coil. The other is to create a coil that is always energized and use a normally open contact associated with the coil. So you have this one, you have this coil, and you have this coil, and it will reset immediately. This one, okay, but it will definitely go here. It will set this one and go up. As long as this one is on. So thus far, so just coming to some of the conclusion. Thus this far, we have dealt with either ladder diagrams having only one rung, multiple rungs, that may be rearranged in a desired order without affecting the execution of the program. These have served to solve our problems, but leave us limited in things that can be accomplished. Before moving ahead, let us review the steps taken by the controller to solve a ladder diagram. After the IO update, the controller looks at the contact portion of the first run. This logic is solved based on the states of the elements stored in the memory. So this includes all inputs according to the input image table. Okay, and the last known state of all coils or output in internal. After the contact logic has been solved, the coil indicated on the right side of the rung is either energized if the solution is true or de-energized if the solution is false. Once this is accomplished, the controller moves to the next rung logic and repeats the procedure. The coil of a rung, once set or set, will remain in that state until the rung containing the coil is again solved with the next scan. If a contact associated with the rung is used in later rungs, the condition of the contact, energized or de-energized, will be based on the state of the coil at the time of the contact usage. For instance, suppose the coil CR1 is energized in rung 3 of a ladder diagram. Later in the ladder diagram, say at rung 25, a normally open contact CR1 is used in the control over coil. The state of contact CR1 will be energized because coil of the relay 1 was energized in the earlier rung. The normally open energized contact will be closed for the purpose of solving the logic of ladder rung 25. After a rung logic has been solved and the coil set up accordingly, the controller never looks at the rung again until the next scan. Okay, so let's go to the next diagram and see what you mean. We have this one and you check this rung. So here it was energized. When it finds here, it will already be closed. So this will definitely work out. Okay. So these are just things you'll be reading. Just what I've just explained. So a table is shown below. The table takes into account all possible combinations of inputs. The table is filled with each rung as solved, and each line of the table represents solution of one rung logic. So line 1 indicates the condition of the inputs and calls at the time of the controller started. Okay. After the update, all calls begin in the off condition. Line 2 shows the condition of the element after the solution of rung 1 assigning, assuming that in1 was on the last update. Then line 3 shows the state condition of the elements after solution of rung 2. The input 1 remains on for rungs 2 and 3 because of the update that was done before. So these are some of the PLC memory logics. So these are registers in the PLC. These are memory logics. And this is what they represent. After the first read, all of them are 0. The second read, input, then the third read, output 1 became on. The fourth was a reset. Then fifth, that is like all of them are 0. And this is what we're talking about here. So this is a rung we're talking about. Yeah. So those are some of the things we're just giving you a glimpse of what happens in a PLC. So these are some of the review questions I expect you to tackle. That was chapter 3. Okay. So chapter 3 is over. And now we are going to do what we call, we are going to the software version of the PLC. The flip-flops, I will not take you through that because that's a bit advanced for people who haven't done logic circuits. Yeah, but of course they are good solutions for handling such. So the flip-flops, I don't think it will be important for guys who are not doing either electrical or digital electronics. Yeah, this is assembly language for those who don't understand what assembly language means. Assembly language is machine assembly language, is a language used for machine. So those are some of the things I will leave out. I won't let you to go into such kind of, it was a crash program. So yes, deal with chapter 1 to chapter 3. All right. Now, I think we've done a lot. And the next thing is you're going to the PLC. We're going to the PLC. And I know guys will be happy here. So we're going to the PLC and there we go. So I want you also guys to be able to note that PLC programming. What is PLC programming? And there are two ways of programming a PLC. Two basic ways. Number one, we program PLC by using ladder logic. The second step that we program PLC is by using functional block diagram, FBD. So in our case, we're going to look at a case study of Schneider. So this is a document from Schneider I will share with you. We are using PLC Schneider for introduction of the PLC. For advanced series, we are going to use Siemens. For basic series, we use advanced series as math function, a very heavy embedded functions. For basic, we are going to start with Schneider Electric. They have a PLC, the PLC I have it here, the Schneider PLC. I have both PLC for Schneider and PLC for Siemens. So you'll be able to interact with them. You'll just be able to get a session. You will develop how this is going to be done. You have examples in the book that I'll share with you, the ones you'll be using to learn. And now you have the Schneider manual. These are manuals I've selected and I've downloaded for you to use. and I expect that you are going to implement those programs, and we are going to submit the programs for marking. And for your own practice, you also need to develop those programs as they have been developed by Schneider Electric for industry academic learning. So you're going to develop the programs as per the guide, as per what the document says, and you're going to simulate. But of course, I will show you a bit of how to maneuver through the program in the next 10 minutes, 20 minutes. So, and then I'll share with you. So the PLC we are using is called Zilio. This is your logic programming guide. This is a programming guide for Zilio controllers. These are how the controllers look. This is the PLC for what we are using. So this is the PLC we'll be using. So these are the PLC we'll be using, and you'll be able to interact with this one. We'll program, we'll do the inputs, you'll be able to actuate the inputs, read values, check the outputs, the relays are on, boom, put a message. Yeah, so you'll definitely, of course, you'll program them remotely. If you want a session, whoever finishes first on the assignments, you say you want to do a demo program. I set up the PLC, and you're going to interact with it. You first simulate your program, then from there we'll create a session with you. We look for some time. I presume maybe by tomorrow is Monday. If anyone can develop a program, it can be ready by tomorrow. You should be able to do a simulation on the real PLC, but of course we'll have to try it on your simulation end. But if maybe for the practical, maybe for the interacting, we can also create some other time if tomorrow will not be sufficient for you. I know it was a crash program. So this is what the PLC looks like, and it has modules. I've told you these are modular PLCs. So you have the PLC itself, you have its modules here. Okay, these are modular. See, even they've given you 0, these are modular. You can add extra modules, communication module, Ethernet module, DPRS module. So these are very sophisticated PLCs, but they have other modules that you can add and perform complex tasks. And this is just Schneider. This is just a catalog for them. All these are PLCs. So they have different memory logic, they have different functions, and sort of so many things. So this is what we are using, this one. This is a small guy, very powerful. And it's even faster than your computer, very powerful guy. So this is what you're going to use. And this is what you need to do for us to program. I have this cable. I got this cable. So I have it here. So these are some of the things you need to buy if you want to really be a PLC programmer. You can buy a cable for programming the PLC, USB to PLC. You can have a Bluetooth interface, a memory card. You have serial link connection for remote controller, communication and field devices. And then you can have a communication and GSM. You can also develop a HMI, human machine interface, where you can actually see graphics, data, you can see trends, how the pressure is changing. You can use the graphic and connect to your PLC, and you can be able to visualize. Same way you're doing it on your browsers and you see those graphs being generated, the PLC can do the same thing. So these are just like PCs, the only that they are big, compact, and very robust. You can see here you're developing a 3D, and yeah, things look good. So, but before that, these are some of the circuits you'll be looking at. These are circuits. Yep. So this is what you develop, and you'll be able to learn these logics and be able to use them. So these are some of the function block. See, these are function block: the timer, timer watch, pulse generator, boolean, add, subtract, compare, max, min. So many functions there. You can't even finish. These are just PLC programs. The logic functions we're talking about, and, or, NAND, NOR, XOR, NOT. We have division, divergence, set, reset, status, archive. Very many. You compare, you add, subtract. You can even have a timing program, an hour counter. I mean, it's enormous. PLC is a very robust. It's a very small animal, but very powerful. Very small device, but very powerful. So without taking much of the time, this is the catalog. Now let me go to the programming. So there are two ways. You can program the PLC in ladder or function block or function block. So these are discrete inputs. If I go to this document, I just click, it tells me these are discrete output. Right? So this is a manual, how you are able to navigate through the manual. For you, you have to read the manual. For me, I'm already an expert, so I don't really need to read the manual, but I'm guiding you how you can use this. This may be a function from the ladder bar. These discrete inputs, these are the contact. You can see here, like if wire this one to this one, that means the input supply, the contact is conducting. These are the things you're just going to see them work now. We're going to do a demo, and from there we expect I will share with you another guide. This is the programming guide. Okay, 200 and something pages. This is something, when you're done with this one, you already know how to program a full PLC, and you can even throw yourself into a factory, a small factory, not a big factory like those who deal with complex things. A small factory can be able to troubleshoot a PLC as long as you understand these, and you're given the program for the programming software. You can be able to troubleshoot. So like this one is non-voltage. This is like a PLC, how it will be showing you the messages and everything. All right. So for this case, I will switch now to the other part, which is now the software, where you guys are very interested in. The programming guide, applications examples, developed by Schneider Electric. So we'll be dealing with two big guys in the industry, and the application are in ladder. So let's begin with maybe a greenhouse ventilation pens, or let's do something like a gate automatic control. Page number 22. See, when I point my mouse here, it takes me to there. So it tells me you'll need how many. This is now what you'll be given, like a task by a consultant. He tells you, I need an automatic gate. A homeowner wants to control and access to this residence by an automatic gate equipped with a dual direction opening and closing motor. So on opening, whether the gate is closed or in an intermediate position, yeah, the remote control signal causes a full opening of the gate. During the opening process, any new action on the remote control stops and restarts the motor. When the gate is fully open, there's a 4-second time delay before closing can start. Closing. During this closing process, if the remote control is activated, or if the sensor detects a motion, the gate is open. As long as the sensor is activated, for example, a vehicle stopped on the passageway, the gate remains fully open. So you, as a programmer, you're being given now, it's you to think, but this is a guide, they are guiding you. So the first input is maybe remote control. The second is for the telling that the gate is closed. The third input is maybe for gate in open position, motion sensor to give a digital output when maybe there's an object, there's a vehicle there. So for this application, what we will require, No specific conditions are required. Yeah. So what you need is just pick a program. Do you look how it look like? This is just a full software. So let me launch the PLC program. You must be having Zilio, the software I told you to download. I hope you've downloaded and you have it. It's called Zilio. So as it opens, it should be opening also on your end, but you're not going to do anything because I want you to observe. So it's opening, it's taking quite some time. Give it time. So the first thing I'll do is create a new program. Which PLC do I want? This one. And I say, you see, this is a programming language. Eh? Can anyone, is everyone able to see the PLC software?
Yes, you can see.
Right. So this is the first input when you open the Zilio. Let me close this one. This is what you want. So we pick the ladder because for our case we are using the ladder approach first. Then we can do the best approach is always using FBD, function block diagram, because it simplifies. It's just using blocks like the AND gate, the OR gate, the NAND, the NOR. Those are gates. You're using direct gates. You're not using wires. You know, by using ladder is wire representation. And I will show you the difference between that, and we'll use one of these one. It's a PLC 24 VDC. We go next, and the screen is loading, and there we are. And we go to our example. Okay, so just be attentive. So we go to our example. I minimize this, and I minimize this one, and we just want to replicate this. That's how you're going to do it on your end. But for you, you need to do a lot of stuff because you're going to practice. I'll just go to my next screen. So let me do this. So this is a PLC program, and you take input 1 in I1. Okay, you come and put it here on this line, first line, and then you take coil M1, this one. I hope you guys are following up. Take this one, put it here. You see, very easy. And you come and wire this one there. Then we take the RT1, RT1 should be somewhere. It's a retentive timer one. You see, there are so many things here. RM1, RT1. Anyway, I'll pick it up. I'll just pick it up. So I'll pick M1. I'll use the Q's. For the RT, I'm trying to get the RT. That is memory state for the RT. I'll get it for you, so don't worry about that. So you see, this is telling you the number of blocks, the number of ranks. So you cannot exceed more than 240 ranks. If you exceed more than 240 ranks, your PLC is full. So your memory is full, and at least try to maintain 80% of your PLC program. The same way like your PC. You don't use like 100% of the hard disk. You leave some space for the PLC to breathe. So this is when you complete the first rank, now if you put another rank, M1, I'm taking this reference for this one. So M1 reference here, and I wire it to Q1. Q1 is up, so you need to check this one. Q1 is this one, signal, check, then you wire it. I just delete this one. Take this one. Take this one and wire there. Go to the next rank, I4 and T1. T1 should be somewhere. T1. Then I wire this one. So if you click, disappears. So T1 is going to I3. T1 is going to I3. So there is I3 somewhere here. So a circuit is forming up. I go to Q1. Q1 input. And I wire it to I3. And I take it to T1 coil. So that's the coil of the timer. I wire that and I complete my circuit. I click this one to disappear, to remove it. And I'm not going to T this RM1. I will not go into it. I think we'll just generate it some other time. Go to T1. Coil. We take it to I2. Y to I4. Change the state to normal closed. So you click, change. You've seen that. Click here to delete this one, click to connect, no, delete this one. Then I4 is going to Q2. This for set. No, this is not set. Set is wrong. Let me change this one. Something is just up. It's a window which is open. Where is this window? So window is open. No, it's opening from. Yeah, it's off. So okay. So I'm deleting this. I'm putting Q2 coil. Even this one, we are giving it a pulse. It is Q1. Okay. So guys, we have our circuit here, and we can so these are just the different windows. So you can, if you go to configuration, you can change the time at T1, how many seconds you want it to come on. For the text, maybe you want to name your input as, say, like what they were saying. I'm just show you something. Motion sensor. Not this one. It's for the gate. control. You want just to name. Can't paste. Remote. So this is get closed. Get open. You have motion sensor. So these are just some of the, these are your name. You have your queue here, inputs, get opening. These are you label them, get closing. And we save. So go to saving them somewhere on Drive, Zilio, programming tunes. This is the motion. Just get opening, get automatic gate. So that is the automatic gate. Save it. Go to configuration. This guy. Anyway. So I'll just go to the video entry. This is how the PLC looks like. And of course you can be able to understand what's happening. So let's go here, and so once you're here, see, you can export this, can expose this, the naming. Yeah, you can just click this and you see what's hidden here. So now we go to simulation is here at the top, this one. So there are 3 states. So you have stop mode, run mode. So the PLC is on, it's ready, but it's not running. So it's powered, yes, but it's not, it has not started working. You want to start it out, you just click run. And you see it changes state. You can pause the PLC. PLC is still on, but it's paused. So PLC is like a machine, it just give it commands. You can resume operation. And as you run now, you can now be able to, if you put this one on, M1 is on, all right? So you see M1 was on, and then this M1 became active. Let me just again disengage. If I put on, check what's happening to M1. All right. And now if I go again put FM for motion sensor, now there's a vehicle coming in. I put the vehicle on. Okay. It's a motion sensor detected as sensor. And now the gate is supposed to open. So the gate has opened M3. When the gate is opening, the timer is already on. So the gate is opening and there's a countdown time. Of course, our timer is 0, that's why it's already engaged, because this is a coil referencing to this one. Okay. And then I2 is gate closed position. When the gate is already in closed position, and the motion sensor, maybe say the motion sensor is still on. So Q2 now becomes on. when Q2 gate is closing, the motion sensor I4, you saw this logic. You saw something coming. See, I4 is here. So closing because motion sensor is off. This Q1 is on. I4 now becomes open because of the reference of these. Because the motion sensor now is already active. The motion sensor is not active because the gate is closing. When the gate is closing, the motion sensor becomes inactive. If the gate is open, everything is ready to begin. These are the switches you use. You press this one, gate opening, timer is counting and elapses, and the motion sensor is still on, it counts. Check here. So the vehicle is passing. The gate is now open. And if now the motion sensor is off, the gate closes and the motion sensor disappears. And now I3 is gate opened position. The gate is open, fully open. Now our timer should go off. Yeah. So when our timer is off, that means the gate is now waiting for the motion sensor to come on. Right. And this is how you do. You see, if you check here, you enable this, you enable that. These are, if now you M1 is just like a memory logic. It used to, for us to, maybe it's a remote start. This is now for the key start. You want us to be able to start the entire circuit. If I don't start it here, the entire circuit will be off. Okay. Yeah. So, I hope you've seen what has happened. It's very easy for you to generate this program. And I'm going to share with you the manual, this one, the program codes. And you're going to generate them. You're going to use these guides from Schneider. And you develop these programs. And you're going to save them. How many programs are they? Let me check. How many? These are 4 programs. What we've done is just automatic. This is what we've used for your demo. So there are how many? 1, 2, 3, 4, 5, 6. You will do them in ladder, and then we'll also do, tomorrow we'll try and do FBD. When you have the 2 scenarios, FBD and ladder, you'll see the difference. Then from there, FBD is very simple to program and can handle complex PLC programs because it reduces the blocks, the memory sizes. You see, for the blocks, these one rows, you are limited to 240 rows. If you exit the rows and maybe you're doing just 1 line of code and you can't minimize maximum the code, you're wasting the ranks. These are now the ranks. The ranks are actually the rows. So you can only do up to 240. After 240, you are out. And you can click on these inputs here. If you click on inputs here, you can also check on the outputs. If you click here, you see everything. And this shows what is happening. Okay? This is the logical representation. And this is the watch. All right, so if maybe we say I1 on, you want to see Q1. If Q1 comes on, that means M1 is on. And gate is opening. See, at Q1 will open, Q1 will come on. So you see Q1 is lighting. So this is some of the how you can be able to know your program and be able to see if I switch is on, I3 is on. So all these inputs are on. I can try to remove them. At some point, you see this one is enabling Q1. Okay. So these are some of the tools that you use, but you actuate them by doing this. You click here, it comes up, pops up. Here pops up. Okay. Even this one is the M the M coils, the memory coils, they are here. So you pop them up and you're able to see everything. And yeah, that's how you're able to. So what I expect from you is try and to see if you can be able to practice on the ladder. I'll share with you this document. It will be a practice document, and the marking will be that for you to have completed this course, you need to develop these applications using the guide. And then you can look at the reference notes, but the reference notes were just for guiding you to learn. I'll also say the reference note materials, but your course is just demonstrate using this one that you can be able to simulate, generate these programs with the following in FBD and ladder. And once you're done with that, we're going to do I'll do the marking and check if you guys have done the correct thing. And from there, maybe you can now organize for how we can be able to maybe issue certificates to those who have completed the course well. We can prepare a certificate to showcase that you at least understand the basics of PLC programming. You can do simulation, you can generate a simple program, you understand what ladder programming is, you understand FBD, you understand simple logic, input and outputs, analog inputs, analog outputs. So such kind of things is what I expect after the course completion. And that one will mean that you have to do practice on your own now that I've given you the software. So you have to practice on the software. These are real industrial software, and the PLC is here. So once you're done the simulation, we can now create another session where you can now be able to, I'll set up the PLC, and now you can be able to load your program on the PLC and be able to actually check what's happening on the PLC. Yeah. So having said that, I welcome any questions because today's course lesson is over. Tomorrow we are going to do the FBD programming, and yeah, you can be able to proceed from there. So thank you for listening. Any questions are welcomed. I know I've taken much of the time because I need, the setting up and the PLC programming is something I needed to teach you today, so you can start learning from the word go. So any questions, any comments, anything? It's your time now.
Hello.
Yes, hello.
Sorry, I don't have a question, but I was just wondering if you will be able to share the video after this.
Yes, I think Ben, are you recording the video session? Or Beryl, who's recording in terms of recording of the video session?
I think Chris is on recording the sessions. We'll post them on YouTube and share the link to the group once they're uploaded to YouTube. Yeah.
Okay.
Thank you.
All right, you're welcome.
Yes, thank you, Jared, and always a big appreciation for the much time you're taking to take us through this. My obvious question was going to be how we're going to simulate this, but I can see you've come up with a very good solution on, first of all, simulating, and also creating the time schedules for us to directly push the code remotely. So yeah, it's a big plus on your side and on our side too. So my next question is this: if your truth diagram is going to become larger and larger enough, as you shown me, are you going to represent this in form of the hexagonal representation or octal representation, or how is it going to be?
Yeah, of course. Every logic truth table is binary. So it's basically binary, and from binary you can use the K-maps to K-map is a tool. Let me show you what a K-map looks like. It will be able to analyze any combinational logic circuit, whatever the size. You give it the things, and it will be able to work out, and you'll be able to do do. There are also online tools, other online tools apart from the KMAP, but KMAP is one of the most powerful tools for PLC programmers. It's developed by some German guy. And so how it looks like, let me just pull a window here. This internet is really messing up stuff. So it's a KMAP is actually what they're talking about is it's technique for Boolean like simplification. So it's actually for digital electronics for those heavy PLC programmers. And this is how it looks like. You have your arrays, so you can, this is for a four input table, and it's able to analyze 16 inputs. If you have a 32, you have to have A, B, C, D, E. A, B, C, D, E, F. Okay, D, E, F. So those are like for 32 inputs. If you go for 64 inputs, you are going to have A, B, C, D, E, F, G, H, I. So you'll have square of those. And then the KMAP will be able to do the computation for you and give you a simple logic. You see, like here, it does a combination. So what it does is you say you want the inputs, it will check the equivalent, then it will write for you the logic simplified, the version, the output, and then from there you generate, you get the min terms, the max term. I think these are digital electronic things. And then from there, once you get the min term, then maximum, max terms, you represent them. And then from there you can group. It's binary computation, algebra. And from there now you see what we're coming up. This is expression group 1, group 2, blah, blah. So this is now what is the output. This is the output for our expression. So this is now what you'll feed in the PLC. You'll feed this function to the PLC. So you see this is this is not fully simplified, but now this is the actual simplified version, the final. So now when you take it, lose it to the PLC, you just have A, B, C, D. You put a note, and you and you get your out. And this is what basically you'll just pick from here. You pick it directly to your PLC logic. You put your A, B, C, and your Q. Maybe your Y is your Q1 or relay 1 or pump 1. So depending on the state of the sensors. So the sensors are like A, B, C, D. Depending on the state of the sensors, what you want to achieve, that's what you get. There's so many other functions. It's just a bit random. So it's a very powerful tool for advanced programmers who are dealing with very complex systems. But we can also use it for simple programs. I mean, if you don't want to really like, so like this one is for, it can even analyze it's not limited. It can analyze so many circuits and give you output on any table. So yes, it has to be binary. You can't deal with octo or whatever. Binary does deal with, because the computer understands only zeros and ones. PLC understands zeros and ones. The rest, it's for the human to interpret what the zeros and ones means. I hope I've answered your question.
Thanks.
Okay. So any other person or any other comment?
I have a question on the software that you're using. There's one I've seen, PLC schematic software for Siemens, and they basically do, okay, for the procedure, I've seen how they probably start by selecting the power supply and then a few other things, the rack, the power supply and all that. Do we also do that for this one? Because I've seen we've done something different. We've just gone directly to the ladder logic without selecting.
So this is for simple automation. Simple automation, you don't need to go to that complexity. This is for simple automation, basic. If you go now to the Siemens higher version of even the higher versions of Siemens, the higher versions of Schneider. Schneider also have a higher version of PLC. They're called, we have the M series, the M40, M60, M240. These Zelios are just the small ones. Even like for the one for Siemens, we also have the small version which is called Logo. We'll do that one as an advanced programming for the advanced or basic controls. But you don't need a power supply. You don't need a power supply included because it's for basic automation. So they don't want to complicate lives too hard because you don't want to scare people. For small automations, just wire the logic direct, get your power supply from some. But of course, for complex, that's for advanced PLC. That's why you see they have to pick a power module they put there because you're going to do that in a rack. You're the one going to do. So when you're deploying the system, you'll come up with the rack, the modules, how they'll be placed, then you print out the design and you give the guys doing the assembly. They will use that one to include. It will also give you, like what we call, what is it called? It's called the distances, even the module sizes. It will actually give you everything. So let me try and see if we can get that tool. Just a minute. And that's why I insist that the organizers, have these items recorded because this is very important training and you need to keep history. So for the organizers, I insist they have to be recorded. I did not want to record from my end because I just decided to give you a task and assignment. So if you guys are going to lose all these information, it should be a big blow on your end. So this is what we call TIA configuration tool. Let me show you something. This is for Siemens. Schneider, let me show you for Schneider. And show you how what beryl means. Schneider PLC selection. No, it's called PLC configuration. All these things are online. It all depends how smart you are, how fast you are, how fast you can be able to adapt to changing technology and find out these tools. But they don't come. You won't sit there and wait for the tools to come for you. You have to be really going far and beyond your comfort zone. So you have to find these tools. Tools are there. They are there for people to use. And just give you a typical example. So for the PLCs, you have simple logic, smart relay. You saw here. So this is what we mean. These are simple logic. Very simple. You go to advanced. Go to advanced, you select maybe like this guy here. This guy here. Okay. You add a power supply, 24 VDC. Like say you select an advanced, how many IO? 20 IOs. Then you go to number of embedded IO in the input, that's maybe say minimum 8. Digital output transistor type, let's see what it will come. Then continue. Still one thing missing, you haven't completed the logic source. There's one thing you need to complete, your connectivity, IoT, Modbus TCP, TCP server. So let's see, there's one thing remaining. One thing remaining, number of devices, 16, I think. Communication, OPC-UA. I told you about OPC-UA server, the web server. But let's do OPC. So OPC is what I told you, the tool that we use. Okay, for using that. So what are we missing? Is there any answer we are meeting? No. So we now go to need to go to continue. PLC selection. Something we need to select. We're missing something. For supply, we selected. So we've selected that one. Now that we proceed, next. So this is what you find in the what Beryl was asking about. So you see now this one generates the components for you. It gives you, you can add a module, maybe a communication module with maybe this one. Add one module, you can add a power supply. Generates a lot of, these are online tools, so you can just use them and they can give you a summary of what you need. You can select something, maybe digital input safety module, this one, and you add, you generate the whole list. So if you're doing advanced programming, you're really like into serious stuff and you want to do a project, you use this configuration online. They give you everything. They give you the part numbers, the bill of materials, they give you the power supply, everything. Yeah, so Schneider also, every manufacturer has this kind of tool. This for only advanced applications. For simple applications like the one we have been doing, you don't need to go to this hassle. No, this is a lot. You might crack your head for a very simple opening gate application by doing this. Yeah, so only recommended for advanced programming. That's where you have more than 20, 30 inputs, or maybe the logic is so complex. Yeah. So have I answered your question?
Yeah. Yes, you have. Thank you. So I have another question on the inputs for the software that you've been using. It's called Zileo Soft, I think. Yeah. So
Yes.
how do you represent the analog inputs in case you have any that you want to use?
For that one, you have to go to the configuration now. You have to start a new project.
Uh-huh.
You get to new. And now you select. You begin that, and then you select the modules. Yeah. So you say maybe you begin this one, you take 0 to 10, tier 0 to 10. Let's go back. Analog. There are those that can not support. Yeah. So like, if you go back, this one cannot support analog modules. Sorry, just went off. So this one, you see, like to go next, it just fits. It cannot support any analog modules. All right. So the PLC, this yes will support. This one is just ladder. Maybe if you go with this one, that's your ladder. If you go next, it tells you how you see. You can add this one, inputs for integer. So you can communication you want to do is used in the program, at least limited device. Can add another one again. Crash. Oh, and now this is just FBD. Does not use ladder. It's advanced. For advanced functions, you can only deal with the FBD because FBD minimizes the program. Called the program size. So like you see, this is an AND, and I'll pick I1, I2, I3, I4, and I bring the slash here. Let me just do something quick. I put here another I, yeah, very quick. I put another I put another analog input. Maybe it's IC. You see, when you see IC, IEE, it means it can either take an analog input or not. So you can now wire this on direct. Very fast. Very fast. The AND gates, these gates reduce your programming time. You just drag and you make your work easier, other than the ladder. The ladder is very simple, but very cumbersome when it comes to, if you have a big program, it was a ladder diagram. It could be like a cable is already here. You already have one line. But now with the AND gate, you can have like, how many ANDs can you have here? So many of them. The OR gates, the SFC, the whatever. So there are so many things you can have here. Yeah. So they just minimize. This is a timer. You can have a timer here, so many, like even 10, 20, so many, and you can develop a very big program here. Just having to use the ladder, because the ladder will limit you to the number of rows, and the program size will be limited as well. So like I said, for the, maybe you want to get an out, an analog out. See, this is an analog out. Yeah? This is an analog out output module. So we need to get something like it's analog. So A out. Yeah, you see this is an still compatible. Let me check another one. Yeah, that's an analog out. So you pick an analog out, and then maybe you have an input analog in. It's analog, maybe from a sensor, and you pick it directly to the analog output. How you now, for most advanced, for the analog inputs, all of them can be done in LAD, in FBD, and not ladders. Yeah. So I think I'm done with that. That's clear, Beryl?
Yeah, I've gotten the point.
Okay. So if there are no further questions, kindly have have the recordings be prepared enough in time, and then by Monday so Kesho, tomorrow we are going to do FBD, and then from there you'll work on your own. You follow the examples that I've shared with you, and you develop the programs. We will do and simulate them here with you guys, and yeah, from there we can see who really understands, and from there we can see, you can be able to be sent to somewhere you can be able to troubleshoot a PLC. This is how you gain skills by learning. So you can program any PLC as long as you understand the basic logics. The program is universal for all. PLCs are universal, so the language is the same, whether it's FPD, LAD, graph, assembly, it's all over, it's the same from one PLC to another. You just need the PLC, the programming software, and the transfer cable. That's it. And the logics are same, standardized all of them. Functions are standardized. So that's the beauty about PLC. When you have a standardized way of doing things, it becomes a bit easier for you to do something rather than having different versions of, I don't know, this one, different variants. You know, like people come with their own versions. So unless there's someone with a burning question. If none, I think you have an assignment. Ensure you start working on those software, familiarize yourself with the software well. Expect that by the end of next week, I will have something from you guys for the material that I'll share, the tutorials on the program you're going to develop, and we can have them review, we see if you understood the concept and you're able to deploy. From there, we can see how we can do now plan for advanced series using Siemens. So we'll go, and then from there we can see if we can now advance to advanced of advanced. We're now going to bigger PLCs and see the power that they come with them. So play around with the software. So the PLC is just beginning, just to start, but after that you need to learn communication, integrating in the IoT, whatever, industrial communication, industrial IoT. There's a lot you can learn for PLCs, but you need to start from somewhere because PLCs are advanced. They're becoming smart. PLCs now will become smart. They will be communicating with every other sensor. Every other sensor will have an IP or maybe a key or identity. So you know that the PLC is just looking for this sensor which is not available. You get it on your phone because through IoT, and all the sensors will be smart. PLCs will be smart now. They will be equipped with smart capabilities. They're able to do so many things. So after that, I think I'll wind up here because we already passed time. 30 minutes. Stick to the time. So we meet tomorrow unless there's any burning question.
I don't think there's any other question. Just a vote of thanks to you, Jared, for making time today. And just teaching us the basics of PLC once again is not something that most people do or do for free. And we just want to thank you once again for that. And also to thank all those who attended this session. And if you've not registered for this event, register using the link that was sent to the group yesterday. And also invite your friends to come. If you know anyone who's interested or anyone who's doing the attachment right now in any industry, I'm sure they're interested in learning PLCs. Yeah. So just share to your friends that they can also attend this event. Thank you, and let's meet tomorrow. Yeah.
Okay, thank you. See you guys. Have a nice evening.